first of all, thanks to the organizers for inviting me. It's great to be here on a little bit longer notice than for 2 years ago when I had like 3 days notice. But anyways, today I will talk a little bit about what we're doing in my group in Trondheim, which is we're starting to use density operators. But rather than going into the details, a lot of it will be motivating why we would do such a thing. Okay, so I'm interested in electronically open systems, and the question is, when is a molecule an electronically open system? Because if you have, for example, 2 water molecules all alone in the world, they constitute an electronically closed system. There is some sort of charge transfer in between the two, but it's overall closed. However, if you come to the point where you're doing things where you can only treat parts of your system explicitly, then you're actually having to deal with an electronically open system. So for example, here I can treat one of the water molecules explicitly, and the other one is sort of an environment that is there, but I cannot include in my quantum mechanical calculation. Then my system of choice is actually an electronically open system. So just to show you a simple example of that, I made a CCSD calculation of the water dimer in a CCPVT basis, but using a local molecular orbital basis. And in a local basis, the orbitals are centered either on molecule A or on molecule B. So by grouping my orbitals, I can say that the couple cluster wave function here can be written like a cluster operator which touches only orbitals on A, a part that touches only orbitals on B, and the mixture. And the reference can be written as sort of a determinant of the two spaces. But if I do that calculation, what I can find out is that the most important singles amplitude, which basically relaxes the system, is actually transferring electrons from one molecule to the other. So these type of terms in my couple cluster wave function depletes electrons from A, and so A gains a positive fractional charge, whereas B has a slightly negative charge, adding up to 0, of course. And from the CCSD density matrix, we can quantify that, and it's a rather small change in this simple example, but it goes to show that this is actually not an insignificant change if your aim is to sort of get an accurate description of your systems. So if I could only treat one of these, whereas the other was part of some mysterious solvent, then I would lose out on some information if I didn't keep my system electronically open. So molecules are electronically open because we usually cannot include everything in our quantum mechanical description. And this is obvious to us as chemists if we try to sort of cross or put a boundary across a covalent bond. And this is done in, for example, in QMMM, you do a capping and put in a hydrogen, but you know there is really some electronic openness going on. But with non-covalent interactions, so when molecules are not bonded, maybe even at rather large distances, like a benzene dimer, then electron correlation, in the Lövdin sense, so anything beyond Hartree-Fock, causes fluctuation of electrons between them. And this will be net zero in equivalent systems interacting, for example, a benzene dimer in a symmetric arrangement. But it would possibly be not zero if you have other systems. And some years ago, when I started doing these wave functions, which are not basically like eigenfunctions of the number operator, then people were telling you, why would you do such a thing? And it's always particle conserving and so on. But now, luckily, I've gotten to the stage where people say, naturally, there is symmetry breaking. And it shows that for net zero transfer, even for net zero transfer, electron correlation, which we can detect in the couple cluster wave function, or full CI, or truncated CI if you like, should contain determinants which basically are of anionic cationic character. And traditionally, we use only these types of determinants even when we know we have an environment that we're interacting with. So for example, for a molecule adsorbed on a surface, we would just normally say, if we treated this implicitly by some model, we would just say that this has a given number of electrons and that's that. But if we do the full couple cluster calculation, I did the full CCSD for such a system, and you actually see very well that there is a net transfer back and forth between these two systems. And this is an example, like this type of example is an equilibrium situation where for a given electronic structure calculation, you can just solve the Schrödinger equation and you can extract this information. But then there's the prototypical electronically open molecules. Those are molecules involved in electron transport. Those are non-equilibrium situations. But here it's much easier to accept that electrons are transported through your molecule, so it should not be electron conserving. But I would say that both of these systems, so the surface interaction and this, they have some of the same physics, but it's more easily accepted in this case. So then comes the question. I said I wanted to talk about density operators. So why do we want to use density operators? And that is if we consider a molecule interacting with a large environment, then information is irreversibly lost to that environment. And the molecular state will be accompanied by some degree of uncertainty. So this is if we cannot treat the environment explicitly, so we're treating our subsystem, so in a reduced manner, then we actually, we don't have maximum information, and we need a statistical mixture. And for this, the density operator is the appropriate quantity. Nonetheless, I will spend probably most of the talk talking about wave functions again. So why this detour? And that's because wave functions from electronic structure theory, we know the strengths and the weaknesses of the existing wave functions. We know the limitations of coupled cluster. We know MCSCF, its advantages and disadvantages. So we have a lot of knowledge on that. We also have experience with doing excited states and excited state properties. And we have a lot of efficient code. So that should be reused. So that's why I today will talk about constructing reduced density operators from using wave functions. And today I'm only going to talk about basically exact state analysis. And for simplicity, only talking about non-covalent interactions between the system and environment. This is described in a paper we just submitted. A short detour work I will not talk about today is reduced density operator from coupled cluster wave functions. We have work in progress on that. My postdoc Alice is working on that. But all of these density operators formalisms, the one I'm going to talk about today, they are primarily designed to be perturbative approaches for the non-covalent interaction. But we also have wave function models that I've developed that are non-perturbative, where the effects of sort of the electronic openness is directly into the Hamiltonian and can handle more strong interactions, like, for example, covalent bonds. And those are the particle breaking restricted Hartree-Fock and particle breaking unrestricted Hartree-Fock. And we have both ground state energy for RHF and UHF versions, but for the RHF versions we also have properties. Which is also a work in progress. Jakob Pedersen, who's also shared with DTU, is working on that. Okay, so let's get to business. What I want is a reduced density operator for the molecule, and I want it to be constructed from wave functions I know strengths and limitations of. But doing exact state today, I'm going to just do first analysis of the full molecular electronic Hamiltonian. Then I'm going to construct the many electron bases to use and construct the projection approach to generate the reduced density. And then I'll talk very briefly on how to deal with the environment. So the full Hamiltonian. We have our Hamiltonian is if in a local molecular orbital basis, orbitals are centered here and here. They don't need to be local within the separate systems, but they need to be localized to either one or the other. And we can define then the interaction Hamiltonian as anything not described in the Hamiltonians which touch only the separate orbital spaces. So this is, for now, the full interaction between these two systems. Then I can use the number operator, which is then just the sum of the number operator for the system and the environment, to categorize the interaction Hamiltonian into two types of terms. I'm going to categorize them into something called PC, particle conserving, and the particle non-conserving, so for short, particle breaking, based on their commutation relations with the number operator for the system. So if the part of the interaction Hamiltonian which commutes with the number operator for the system, those are particle conserving, and the ones that do not commute with the number operator are called particle breaking. And then we can draw the connection to all the sort of embedding and QMMM models that have been developed the last few decades. The particle conserving ones are the ones that you find and are taken into account in all these standard developments. Whereas this part, the one that induces sort of the fact that the number of electrons is not a conserved quantity, that has largely been ignored. So it's been my life mission the last few years. So we focus on this particle breaking term because the particle conserving term I can choose to include in a number of ways. So for now I'm going to ignore it, but we have different ways of including it, like just using standard QMMM like polarizable or non-polarizable, multi-level Hartree-Fock, or like whatever you choose. But I'm just going to look at the particle breaking Hamiltonian. And I'm going to rather to use the full particle breaking Hamiltonian with all its 1 and 2 electron integrals. I'm just going to now write it into an effective operator. Even though we have the expressions in terms of 1 and 2 electron integrals, but this 1 electron operator, or basically this bilinear form, is easier to handle. So here you see you have some orbitals centered on the system. They are with the unbarred indices, and then we have barred indices for the environment. So we're interested in how the molecule is affected by the environment. And by doing so, we want to not treat the environment explicitly. And so I'm only interested in a reduced description of the molecule itself. And here I will also only look at steady state properties and not actual time development. You see, I put in a time dependence here, but that's just the sort of the usual quantum chemistry trick. You put on a time dependence and then you get out the basically time independent properties, but you get excited state properties and these kind of things. So this is just the same trick. I put in a T, but I'm only interested in the steady state. So we have to construct a many electron basis for the density operator. So in this exact state approach, we are using the eigenstates of the 0th order Hamiltonian, so just the non-interacting systems. And there I know that the exact state will come from full configuration theory. And unlike Janus, I'm not very keen on actually computing the full CI states, but they are very nice from an analysis point of view. And unlike usually when you write up full CI, we're also including not just excited states, but also ionized states and attached states and so on. And we construct our many electron bases for the composite system from these two solutions. So here is basically an eigenstate of the system Hamiltonian. This is an eigenstate of the environment Hamiltonian. These two operators commute. So a combined eigenfunction for the full sum here can be done by making a combination of these two states. So then we have a many electron basis. The states are eigenstates of the 0th order Hamiltonian, and now we're going to express sort of what happens when you put on the interaction in terms of this basis. So we can write the density operator and expand it in the eigenstates of the H0, and then of course the time evolution. Now we're not in the Schrödinger equation anymore, but we have to do the Liouville-von Neumann equation for the density operator, written here in the interaction form. So to get the reduced density operator, because this is now formally the full density operator for the entire system and environment. But I'm only interested in my molecule, so I want to like a reduced system description. So what do we then do? Well, there is, from the theory of open quantum system, there is the Nakajima and Zwanzig projection operator approach. So we need a projection operator, essentially. And within this full CI composite many electron basis, we can actually explicitly construct it. So the P operator can be explicitly constructed, and the Q is then just its orthogonal complement. And then we get, using these projection operators, rather than writing one Liouville-von Neumann equation, we can write two equations, and they are coupled. And in the limit of zero interaction, they just decouple to Liouville-von Neumann equations for the separate system and environment. But it's a very convenient starting point for approximations, perturbative approximations. For example, how to treat the environment, which is encoded through the Q projected density. So that's then the question, how to deal with the environment. One simple way is to use red field theory to get a kinetic equation where you can compute rates from a chosen electronic structure model. And you must include broadening of states phenomenologically. And red field is very simple. And as everyone points out to me, you shouldn't do red field, it's terrible. There is NEGF. And of course, NEGF is fantastic. And the standard, for example, in non-equilibrium, like in transport theory, you have advanced and retarded propagators, you wrap in your environment through the Dyson equation, and the broadening can be calculated. So my only issue with this is, of course, that I'm a quantum chemist from the Scandinavian school, and I would much prefer to use response theory. And does response theory have the necessary points? It does. You can do advanced and retarded propagators, you can wrap in your environment, and you can also calculate the broadening as sort of decay rates out of your electronic states. So there are many flavors of treating the environment, and although NEGF is well established, I think that red field as a simple starting point and response approaches are worth considering. That leads me to summarize, to say that in general, all molecules are electronically open unless you actually put them in a severe vacuum. So electronically closed molecule is a special case. And I think that density operators constructed from well-known and loved wave functions are versatile tools. You can describe both pure and mixed states, you can describe equilibrium and non-equilibrium cases, and your system can be open to both electrons and the thing I haven't talked about, of course, energy. So with that, I would like to thank my group, Bendik, Alice, and Jakob. Jakob is shared with DTU, and Regina, who graduated earlier this year, and also my collaborators on this type of work. And thank you for your attention.
Excellent, thank you. I thought we would get away without looking at operators, but we didn't, and it's good. So you say so well in time that we have lots of time for questions or an extended coffee break. Is there a question from the audience? If that's not the... Yeah, here, Joe, go ahead.
So you mentioned the non-equilibrium approach. The non-equilibrium approach, one of the funny things is that, as far as I know, it's only been successful with a one-body Green's function, not a two. Do you know anybody who's done it with a two successfully?
I don't know. I think if there is someone who's doing it or getting close, it must be, or something of those lines, it would be Galperin, I think, in the States. Yeah, I think I don't know. I at least see he's done some strong coupling thing. But I mean, I haven't looked that much into it because my interest is coming from the molecule side and not from the transport side.
Now I want to ask a question because we have so much time. Your statement about every molecule is open, because that also depends on the environment. Now I'm trying to make a wild guess or something. From a perspective of the electrons, the protons are part of the environment somehow, maybe. So I'm wondering, because a while ago we had Sharon Hammer-Schiffer here who made a big point about describing protons as wave functions and how they interact with electrons. In which way do you describe the protons, and would some kind of delocalization of that particle influence the extent to which these are open shells in a dimer of water, for instance?
I think it's a good question about the protons. I mean, as far as I now look at it, for me now the environment is basically molecular, but it could of course be a proton. But then you're in the regime where the proton is not really the environment, it's an integrated part of the system, right? So
where's the boundary? Anyway,
yeah, exactly. So this is more about where at some point you have to be pragmatic and cut. But if there is a proton involved in the reaction, you would never leave it out. Yeah.